Student, excuse me. Can you hear me? Okay, thank you. I your microphone for speaking. Okay. Now you speaking with me by microphone. Okay. We tell you about and dynamic. Okay. We set you part 1 and session 1. So now we must speak about, yes, introduction to the power system stability problem. Okay, chapter 2. Yes. Excuse me now, my voice is better. My voice is better now or no? Thank you. Okay. Chapter 2. Introduction to the power system stability problem. Do you any question of this session? If you have any question, please ask me. Okay. Okay, Mr. Ali Sadeh, no question. Okay. Basic concepts and definitions. Power system stability may be broadly defined as that property of the power system that enables it to remain in a state of operating equilibrium under normal operating conditions and to regain an acceptable state of equilibrium after being subject to a disturbance. Mr. Ali, please turn off your microphone. Okay. Instability in a power system may be manifested in many different ways depending on the system configuration and operating mode. Traditionally, the stability problem has been one of the maintaining synchronous operation. Since power system rely on synchronous machines for generation of electrical power, Mr. Ali Sadeh have any question? Okay, so please turn off your microphone when I speak to you, okay? Okay. Since power system rely on synchronous machines for generation of electrical power and necessarily condition for satisfactory system operation is that all synchronous machines remain in synchronism or colloquially in step. This aspect of stability is influenced by the dynamic of generator, rotor angle, and power angle relationships. Basic concepts and definitions. In the evaluation of stability, the concern is the behavior of the power system when subjected to a transient disturbance. The disturbance may be small or large. Small disturbance in the form of low changes take place continually, and the system adjusts itself to the changing condition. The system must be able to operate satisfactorily under this condition and successfully supply the maximum amount of load. It must also be capable of surviving numerous disturbances of a severe nature, such as a short circuit on a transmission line, loss of a large generator or load, or loss of a tie between two subsystems. The system response to a disturbance involves much of the equipment. For example, a short circuit on a critical element of flowed by its isolation by protective relays will cause variation in power transfers, machine rotor speeds, and bus voltage. The understanding of a stability problem is greatly facilitated by the classification of stability into various categories. Rotor angle stability. is most importance of stability, that is named rotor angle stability. Rotor angle stability is the ability of interconnected synchronous machines of a power system to remain in synchronism. The stability problem involves the study of the electromechanical oscillations inherent in power system. A fundamental factor in this problem is the manner in which the power outputs of synchronous machines vary as their rotors oscillate. Mr. Ali Murad, can you hear me now? Mr. Ali Murad, Kazem or only? Arabuli. Okay. Synchronous machine characteristics. A synchronous machine has two essential elements: the field and the armature. Normally, the field is on the rotor and the armature is on the stator. The field winding is excited by direct current. When the rotor is driven by a prime mover turbine, for example, turbine, the rotating magnetic field of the field winding induces alternating voltages in the three-phase armature windings of the stator. Salamun alaikum, Mrs. or Mr. Mahje Ahmad. The frequency of the induced alternating voltages and of the resulting currents that flow in the stator windings when a load is connected depends on the speed of the rotor. The frequency of the stator electrical quantities in thus synchronize with the rotor mechanical speed. Hence, the designation synchronous machine. Okay. When two or more synchronous machines are interconnected, the stator voltages and current of all the machines must have the same frequency and the rotor mechanical speed of each in synchronized to the frequency. Therefore, the rotors of all interconnected synchronous machines must be in synchronous. The physical arrangement, spatial distribution of the stator armature winding is such that the time varying alternating currents flowing in the three-phase winding produce a rotating magnetic field that under steady state operation rotates at the same speed as the rotor. See chapter 3 section 3.1.3. The stator and the rotor field react with each other, and an electromagnetic torque results from the tendency of the two fields to align themselves. In a generator, this electromagnetic torque opposes rotation of the rotor, so that mechanical torque must be applied by the prime mover to sustain rotation. The electrical torque or power output of the generator is changed only by changing the mechanical torque input by the prime mover. The effect of increasing the mechanical torque input is to advance the rotor to a new position relative to the revolving magnetic field of the stator. Conversely, a reduction of mechanical torque or power input will return the rotor position under steady state operating conditions. The rotor field and the revolving field of the stator have the same speed. However, there is an angular separation between them depending on the electrical torque or power output of the generator. In a synchronous motor, the roles of electrical and mechanical torques are reversed compared to those in the generator. The electromagnetic torque sustains rotation, while mechanical load opposes rotation. The effect of increasing the mechanical load is to return the rotor position with respect to the revolving field of the stator. So, in the above discussion, the terms torque and power have been used interchangeably. This is common practice in the power system stability literature, since the average rotational velocity of the machines is constant, even though there may be small momentary exertion excursion above and below synchronous speed. The per unit value of torque and power are in fact very nearly equal. Okay, now you see power versus angle relationship. In figure 2.1a, we see a single line diagram of a generator and a motor that connected by a line. And in figure B of 2.1, we see idealized model, and in figure C of figure 2.1, you see a phasor diagram of the power system. At the last of the figure, we see a power angle curve that you see this is the power by delta. An important characteristic that has a bearing on power system stability is the relationship between interchange power and angular positions of the rotors of synchronous machines. This relationship is highly non-linear. To illustrate is this, let us consider the simple system shown in figure 2.1a. It consists of two synchronous machines connected by a transmission line having an inductive reactance XL, but negligible resistance and capacitance. Let us assume that machine 1 represents a generator feeding power to a synchronous motor represented by machine 2. The power transferred from the generator to the motor is a function of angular separation delta between the rotors of the two machines. The angular separation is due to three components. One, generator internal angle delta G, that named delta G, angle by which the generator rotor leads the revolving field of the stator. Two, Mr. مايو شمری, Mrs. Please repeat. If you have a question of me, please repeat. Do you have any question? Your microphone is on. can turn off your microphone. Okay. Okay. So you see in this figure, I zoom for you. That delta is equal to delta G plus delta L plus delta M. So delta G is generator internal angle. 2. Angular difference between the terminal voltage of the generator and motor, angle by which the stator field of the generator leads that of the motor, and the internal angle of the motor. Number 2 is equal or named delta L, okay, and 3 is named delta M. That is the internal angle of the motor, angle by which the rotor lags the revolving stator field. So please see again this figure, that P is power is equal to EG EM sinus delta divided to XT. That XT is equal to XG plus XL plus XM. That XM is reactance of motor, XL is reactance of transmission line, and XG is reactance of generator. Figure 2.1b shows a model of the system that can be used to determine the power versus angle relationship. A phasor diagram identifying the relationships between generator and motor voltage is shown in figure 2.1c. The power transferred from the generator to the motor is given by this equal that I said to you in slide, okay? P is equal EG, that is, this is EG, and this is EM, divided to XT, that is equal to XG plus XL plus XM, multiplier in sinus delta, where XT is equal XG plus XL plus XM. The corresponding power versus angle relationship is plotted in figure 2.1d. If you see this figure, you see when the delta is 0, we don't have any power, but in delta is 19 degree. The delta is maximum power. Okay, so with the sum that idealized models used for synchronous machines, the power varies as a sine of the angle. A highly nonlinear relationship. When the angle is zero, no power is transferred. As the angle is increased, the power transfer increases up to a maximum value. After a certain angle, normally 19 degree, a further increase in angle results in a decrease. This is 19, okay? Degree. Mr. Maiyo, do you have any question? Okay. Okay, you see, this is 0 degree, this is 19 degree, and this is 180 degree. There is thus a maximum steady state power that can be transmitted between the two machines. The magnitude of the maximum power is directly proportional to the machine internal voltage and inversely proportional to the reactance between the voltages, which includes reactance of the transmission line connecting the machines and the reactance of the machines. Mr. or Mrs. Roy Maye Javadar Shemri, do you have any question of me? Or do you have any question? Please ask your question. I don't have your voice, but I hear a voice that is not good. Excuse me, student. Can you speak with Mr. Jawad al-Shemri? That turn off your microphone. Yes, I can turn off your Mr. Jawad Shemri's microphone, but he or she turn on again. Okay. Now I turn off the microphone of Mr. Al-Shemri. Okay. The stability phenomena. Stability is the conditions of equilibrium between opposing forces in a system equipped synchronous machines. Under steady state condition, there is torque of each machine and the speed remain constant. If the system is perturbed, this equilibrium is upset, resulting in acceleration or deceleration of the rotors of the machines according to the laws of motion of a rotating body. If one generator temporarily runs faster than other, the angular position of its rotor relative to that of the slower machine will advance. The resulting angular difference transfers part of the load from the slow machine to the fast machine, depending on the power angle relationship. This tends to reduce the speed difference and hence the angular separation. But beyond a certain limit, for example, over than 19 degrees, an increase in angular separation is accompanied by a decrease in power transfer. This increase the angular separation further and leads to instability. Excuse me, student. Excuse me, student. please break time for 5 minutes after this slide. Okay, we go and come back after 5 minutes. Okay. After this slide. Yes, after this slide. With electric power systems, the change in electrical torque of a synchronous machine following a perturbation can be resolved into two components. Delta T equal to Ts multiplier in delta delta plus Td multiplier delta omega, where Ts delta is the component of torque changing in phase with the rotor angle perturbation. Delta delta and is referred to as the synchronizing torque component. Ts is the synchronizing torque coefficient. Td delta omega is the component of torque in phase with the speed deviation. Delta omega and is referred to as the damping torque component. Td is the damping torque coefficient. System stability depends on the extent of both components of torque for each of the synchronous machines. Lack of sufficient synchronizing torque results in instability throughout an periodic drift in rotor angle. On the other hand, lack of sufficient damping torque results in oscillatory instability. Okay. Breakdown for 5 minutes. I go and come back to you after 5 minutes. Okay. Breaking time is now started. خانم Hello, student. I come back you. Can you hear me now? Okay, thank you. Do you have any question until now? از برعکسش کنه تو بازش کنه. Mr. Ali Sadiq Al-Savidi, please ask your question. So far, no. But Mr. Ali Sadiq Al-Savidi write yes if he has any question. Please answer. Please ask. Ask me. Okay. Okay. Lag, lead, and power factor.
محمد باقي.
Okay. If the current phasor of current is the phasor of current is later than the voltage or phasor of voltage, we have a lag system. Okay. At if current phasor of current is ahead of voltage, we have a lead. Okay. Yes, if we have load by inductive load. We have lag in system, but if have a capacitor load, we have a lead system. So if we have inductive load or winding in the system, we have current phasor is later than the voltage phasor, and so theta V, that is the angle of voltage, I write for you V is equal the angle of voltage okay, phi is equal the angle of voltage minus angle of current. But if the phi is positive, so we have lag in system. But if phi is negative, we have lead system. Okay. Okay. So this is positive lag, that if current is later than the voltage, this is positive. But if current angle is ahead of the voltage angle of voltage, so we are phi is negative and the system is lead. So in a system that we have inductive load, we have lag, but if we have a capacitive load, we have a lead. Okay, but non-linear is, for example, sine is the plate of sine is, this is non-linear. But for example, this is a linear. Okay, linear curve. This is a linear curve. Okay, thank you. The rotor angle stability phenomena is divided to the following two categories. One, or A small signal. B, transient stability. A small signal or a small disturbance stability is the ability of the power system to maintain synchronies under small disturbances. Such disturbances occur continually on the system because of small variation in loads and generation. The disturbances are considered sufficiently small for linearization of a system equation to be permissible for purpose of analysis. Instability that may result can be of two forms. One, a steady increase in rotor angle due to lack of sufficient synchronizing torque, or two, rotor oscillation of increasing amplitude due to lack of sufficient damping torque. B, transient stability is the ability of the power system to maintain synchronies when subjected to a severe transient disturbance. The contingencies usually considered are short circuits of different types: phase to ground, phase to phase to ground, or three phases. The resulting system response involves large exaggerations of generator rotor angle and is influenced by the nonlinear power angle relationship. Nonlinear power angle relationship, that is the nonlinear power angle relationship. Or in next slide you see nonlinear. Okay, for a generator connected radially to a large power system in the absence of automatic voltage regulators, i.e. with constant field voltage, the instability is due to lack of sufficient synchronizing torque. This results in instability throughout a non-oscillatory mode as shown in figure 2.2a. So you see the figure 2.2a. Okay, with constant field voltage. If the TS synchronized torque is positive and damping torque is positive, we are stable. So if the synchronized torque is negative, we have instability. So you see in figure. With continuously acting voltage regulators, the small disturbance stability problem in one of ensuring sufficient damping of system oscillation. Instability is normally through oscillations of increasing amplitude. Figure 2.2b illustrates the nature of generator response with automatic voltage regulators. You see? Okay. In this figure, we don't have damping torque, so or negative TB is negative, so we have instability in system. That the figure is this form. Figure 2.3 illustrates the behavior of a synchronous machine when subjected to a serve disturbance for stable and unstable situations. It shows the rotor angle responses for a stable case and for two unstable cases. This is the case of stable, and this is two cases that we have instability, case 2 and case 3. Rotor angle response to a transient disturbance. Yes, Mr. Ali Sadeh, torque of synchronized torque and damp, okay? Not torque, okay. Voltage stability and voltage collapse. Voltage stability of a power system to maintain a steady, acceptable voltage at all buses in system under normal operating conditions and after being subjected to a disturbance. The system enters a steady of voltage in stability when a disturbance increase in load demand or change in system condition causes a progressive and uncontrollable drop in voltage. The main factor causing instability is the inability of the power system to meet the demand for reactive power. A criterion for voltage stability is that at a given operating condition for every bus system, the bus voltage magnitude increases as the reactive power injection and at the same bus is increased. A system is voltage unstable if for at least one bus in the system, the bus voltage magnitude V decreases as the reactive power injection Q at the same bus is increased. In complex practical power systems, many factors contribute to the process of system collapse because of voltage instability. Strength of transmission system, power transfer levels, load characteristics, generator reactive power capability limits, and characteristics of reactive power compensating devices. In some cases, the problem is compounded by uncoordinated action of various controls and protective systems. For purpose of analysis, it is useful to classify voltage stability into the following two subclasses: A. Large disturbance voltage stability. B. Small disturbance voltage stability. Large disturbance voltage stability. Large disturbance voltage stability is concerned with the system's ability to control voltage following large disturbances such as system faults, loss of generation, or circuit contingencies. The ability is determined by the system load characteristics and the interactions of both continuous and discrete controls and protections. Determination of large disturbance stability requires the examination of the nonlinear dynamic performance. Performance of a system over a period of time sufficient to capture the interactions of such devices as underload, tap changing, ULTCs, and generator field current limiters. The study period of interest may extend from a few seconds to 10 of minutes. Therefore, long-term dynamic simulations are required for analysis. A criterion For large disturbance, voltage stability is that following a given disturbance and the following system control actions. Voltage at all buses reach acceptable steady state level. A small disturbance voltage stability. B. A small disturbance voltage stability is concerned with a system ability to control voltage following small perturbations such as incremental changes in system load. This form of stability is determined by characteristics of load, continuous controls, and discrete controls at a given instant of time. This concept is useful in determining at any instant how the system voltage will respond to small system changes. The basic processes contributing to a small disturbance voltage instability are essentially of a system of a steady state nature. Therefore, static analysis can be effectively used to determine stability margins, identify factors influencing stability, examine a wide range of system conditions and a large number of post-contingencies scenarios. A criterion for a small disturbance voltage stability is that at a given operating condition for every bus in the system, the bus voltage magnitude increases as the reactive power injection at the same bus is increased. A system is voltage unstable if for at least one bus in the system, the bus voltage magnitude V decreases as the reactive power injection Q at the same bus is increased. Mid-term and long-term stability. The terms long-term stability and mid-term stability are relatively new to the literature on power system stability. They were introduced as a result of the need to deal with problems associated with the dynamic response of power system to severe upset. Severe system upsets result in large exaggerations of voltage frequency and flows that thereby invoke the actions of slow processes, controls, and protection not modeled in conventional transient stability studies. The characteristic time of the processes and devices activated activated by the large voltage and frequency shift will range from a matter of seconds. The response of devices such as generator controls and protection to several minutes. The responses of devices such as prime mover energy supply systems and the load voltage regulators. Long-term stability. Long-term stability analysis assumes that inter-machine synchronizing power oscillations have dampened out, the result being uniform system frequency. Long-term stability is usually concerned with the system response to major disturbance that involve contingencies behind the normal system design criteria. The focus is on the slower and the longer duration phenomena that accompany large-scale system upsets and on the resulting large sustained mismatches between generation and consumption of active and reactive power. These phenomena include boiler dynamic of thermal units, penstock and conduit dynamic of hydro units, automatic generation control power plant and transmission system protection or controls, transformers, saturation, and the midterm stability. The midterm response represents the transition between short-term and long-term responses. In midterm stability study, the focus is on synchronizing power oscillation between machines, including the effects of some of the slower phenomena and possibly large voltage or frequency exaggerations. Typical ranges of time periods are as follows. Short-term or transient is 0 to 10 seconds, or mid-term is 10 seconds to a few minutes, and long-term is about a few minutes to tens of minutes. It should, however, be noted that the distinction between mid-term and long-term stability is primarily based on the phenomena being analyzed and the system representation used, particularly with regard to fast transient and inter-machine oscillations, rather than the time period involved. Okay, this is the classification of stability. This is an important figure that say about it. So I zoom it, and you see power stability, ability to remain in operating equilibrium between opposing forces. So we have two kind of the stability. One, angle stability, and two, voltage stability. So we can this stability divided to mid-term stability and long-term stability. Okay, but angle stability is the most important. Its ability to remain to maintain synchronous torque balance of synchronous machines is transient stability divided to transient stability and small signal stability. That the transient stability is large disturbance facing a periodic drift, a steady period up to 10 seconds. But a small signal stability is divided to non-oscillatory instability and oscillatory instability. That insufficient synchronizing torque, but in oscillatory instability is divided to insufficient damping torque, unstable control action, but divided to local plan modes, interior mode, control mode, and torsional modes. But the voltage stability is divided to two kind of stability. One of these is large disturbance voltage stability, and two is small disturbance voltage stability. That the largest disturbance voltage stability is large disturbance switching events, dynamic of ULTC loads, coordination of protection and control. And in a small disturbance voltage stability, we study about steady state, reactive and active and reactive power, voltage relations, stability margin, Q reserve. With availability of improved analytical techniques, providing a unified approach for analysis of fast and slow dynamics, distinction between mid-term and long-term stability has become less signification. That C classification of power system stability, that important figure. Okay, instability of a power system can take different form and can be influenced by a wide range of factors. Analysis of stability problem, identification of essential factors that contribute to instability and formation of methods of improving stable operation are greatly facilitated by classification of stability into appropriate categories. These are based on the following considerations: the physical nature of the resulting instability, the size of the disturbance considered, the devices, process, and time span that must be taken into consideration in order to determine stability, and the most appropriate method of calculation and prediction of stability. Okay, the chapter 2 is enough, but now we start the part 2 that is about equipment characteristics and modeling. Okay, do you have any question until now? Okay, thank you, students. So I start for 2 or 3 slides about this chapter and this season, but in next session we said about it bigger. Okay. Part 2, equipment characteristics and modeling. Chapter 3, synchronous machine theory and modeling. Synchronous generator form the principal source of electric energy in our system. Many large loads are driven by synchronous motors. Synchronous condensers are sometimes used as a means of providing reactive power compensation and controlling voltage. These devices operate on the same principle and are collectively referred to as synchronous machines. As discussed in Chapter 2, the power system stability problem is largely one of keeping interconnected synchronous machines in synchronies. Therefore, an understanding of their characteristics and accurate modeling of their dynamic performance are of fundamental importance to the study of power system stability. Mr. Hassouni, I set you in next lecture, but just 2 or 3 slides about synchronous machine I said and so it's good for you. But if you tired, I can finish this session. Okay, if you are all of students are tired, we can finish for this session. Okay, do you have tired students? Please answer me please answer me by yes or no. Do you have okay, it's just 2 slides. Okay, yes, just 2 slides. Okay. Yes. Physical description. Figure 3.1 shows the schematic of the section of the 3-phase synchronous machine with 1 pair of field poles. The machine consists of 2 essential elements: the field and the armor. The field being carries direct current and produces a magnetic field which induces alternating voltage in the armature winding. You see, this is the winding for phase A. This is A prime, B prime, and C prime. This is the rotor and this is the stator. Okay, you see, this is stator, you see, and this is the rotor. These are the field winding that turn over the rotor. Okay. So this is axis of phase A is if the A winding is this, that axis of phase A is this, that D axis and Q axis you see in figure. Okay, schematic diagram of a 3-phase synchronous machine. Yes, Mr. Faten Mohsen Hassan Al-Ameri. Don't worry. Don't worry. I helped you in the final exam, but you must study very good. Okay, thank you. Last slide is armature and field structure. The armature winding usually operate at a voltage that is considerably higher than that of the field, and thus they require more space for solution. They are also subject to high transient current and must have adequate mechanical strength. Therefore, normal practice is to have the armature on the stator. The three-phase winding of the armature are distributed 120 degrees apart in space so that with uniform rotation of the magnetic field, voltage displaced by 120 degrees in time phase will be produced in the winding. Because the armature is subjected to a varying magnetic flows, the stator iron is built up of thin lamination to reduce eddy current loss. So now the slides are finished and a lecture is finished for this session. Okay. If all of the students have any question, please ask me. But if they don't have any question, we can exit the class, and so class is finished. Do you have any question?
السلام عليكم. السلام عليكم. بالبساط بالبساط. بالبساط.
Thanks, dear Rana Kamel Jafar Al-Wasiti. Thanks, Haydar Ibrahim Ismail Al-Saidi. Thanks, Osame Jahad Jabir. Okay, thanks for all of the students. You're welcome, and best regard for you. Shukran, shukran jazira. شكرا.
روح تذكر كتابك واشتغل البغداد. انت شنو الواد ما تعرفه؟ انت متخصص هناك.
شكرا. Goodbye for students. Goodbye. خدا حافظ. Thank you. خدا حافظ. Goodbye.
هذا قال goodbye. اكتب له goodbye. اكتب goodbye. راح اكتب اثنينك يلا goodbye. اكتب حياني. good باي. كتبت باي. انت دوبك ما تشوف، ما توجد من كيف القفاز. يوم قلت لك ما توجد، شوف الرواية. لا تعمى عيونك. لا لا، وصلت هاي اجتني هاي حالات احلى من مالتي. شو هاي احلى من مالتي. مو بصفى عمي، مو انا قاعد اترجم عمي، طلاب دراسات عليا عمي، والسالفه فشله.